Let us begin very gently with one of the oldest and strangest questions in mathematics. A person wants to move from one place to another. Nothing could seem simpler. To walk across a room, to run down a track, to reach a finish line, to move a hand from one point to the next. Motion feels immediate, ordinary, almost too familiar to notice. And yet, when certain philosophers in ancient Greece began to think carefully about motion, they discovered something deeply unsettling. They noticed that before you can arrive somewhere, you must first get part of the way there. And before that, you must get part of the way to that part. And before that, part of the way again. Again and again, the distance seems divisible into smaller stages. There is always another before. There is always some earlier portion that must be crossed first. And so a troubling thought appears. If motion requires passing through endlessly many intermediate stages, then how can motion ever be completed? How can someone arrive anywhere at all? How can a race ever finish? How can an arrow ever reach its target? How can Achilles, fast and powerful, ever catch a slow tortoise if the tortoise has even the slightest head start? This is the atmosphere of Zeno's paradox. And it is worth lingering here, because the paradox is not childish. It is not a simple confusion that modern people can laugh away. It is an honest confrontation with infinity. It asks how an endless structure can fit inside an ordinary event. It asks how infinitely many stages can belong to a finite act. That is why the paradox feels so disturbing. It is not merely about running or walking. It is about the relation between endlessness and completion. It is about whether the mind can make sense of a process that seems to go on without end, and yet somehow produces a finished outcome. Let us stay with the most famous version. Suppose Achilles runs after a tortoise. Achilles is faster, much faster, but the tortoise begins a little ahead. Before Achilles can catch the tortoise, he must first reach the point where the tortoise began. But by the time Achilles arrives there, the tortoise has moved a little farther. Then Achilles must reach that new point. But again, the tortoise has moved slightly ahead. Then Achilles must reach that next point. And again, and again, and again. So it seems there is an endless list of tasks. First this point, then the next point, then the next. If there are endlessly many such tasks, how can Achilles ever complete them? And if he cannot complete them, how can he ever catch the tortoise? Another version is even simpler. Before you can travel a whole distance, you must travel half it. Before that, half of that half. Before that, half again. At each stage there is another stage before it. The path seems to dissolve into an endless chain of prior requirements. Now, what is important is not to brush this aside too quickly. The paradox is powerful because the reasoning feels clean. Each step seems plausible. If you must cover the whole distance, then of course you must cover the first half. And before covering that half, perhaps you must cover its first half. The logic seems difficult to resist. So the question becomes, where is the resolution? How can something involve endlessly many stages and still come to completion? Modern mathematics answers this question not by denying the endlessness, but by learning how to speak about it properly. That is the great conceptual shift. The paradox becomes softer and then clearer once we distinguish two very different things. One is the number of stages in a process. The other is the total amount accumulated by those stages. These are not the same question. Endlessness in the count of stages does not automatically mean endlessness in the total result. It is worth repeating that, because it is one of the central lessons of analysis. An endless number of stages does not necessarily produce an endless total. A process can have no final stage and still have a finite overall effect. Infinity here is not about a giant object sitting all at once before us. It is about the process unfolding step by step, refinement after refinement, stage after stage. This brings us toward the modern language of limit. Before speaking about infinite sums, it helps to speak about sequences. A sequence is simply an ordered list that unfolds term by term. Not just a collection, but a collection with order. First one value, then another, then another. A sequence records a process of generation or approximation. It is one of the basic ways mathematics studies something that continues. A very common first example is the sequence consisting of 1/2, then 1/4, then 1/8, then 1/16, and so on. Each term is half the previous one. Each term becomes smaller. The values do not jump around wildly. They move in a clear direction. They sink towards zero. Now notice something subtle but essential. None of these terms is zero. Not the first, not the second, not the 10th, not the 1000th. Every term remains positive. Every term remains distinct from zero. And yet we still say the sequence approaches zero. This is an important moment. To say that a sequence approaches a limit does not mean it must equal that limit at some finite stage. Convergence is not the same as arrival in the ordinary physical sense. In analysis, approaching is enough, provided it becomes exact in a precise way. The sequence can converge to zero without ever literally becoming zero at any finite point in the list. That idea can feel strange at first, because ordinary language often treats approaching as vague. One says something is near, or getting closer, or almost there. But mathematics does not allow itself to remain at the level of poetic suggestion. Mathematics asks, what exactly does it mean to get closer? How close? From when onward? In what sense is the closeness stable? The concept of limit answers these questions. Informally, the limit of a sequence is the value that the terms can be made as close to as we like, provided we go far enough along the sequence. There is no fixed level of accuracy built into the idea. The closeness must work for every margin, even the tiniest one we choose. The sequence does not merely flirt with the limit now and then. It eventually remains close. Their phrase remains close matters. Convergence is not about a few accidental near misses. It is about sustained closeness from some point onward. After enough stages, every later term stays within the desired margin. The sequence settles into nearness. It may never coincide exactly with the limit, but it becomes locked into arbitrarily fine proximity. Let us pause and reflect. A limit is not just a guess about where values seem to be heading. It is a disciplined statement about long-term behavior. If the sequence converges to some number, then for every small tolerance we name, there comes a stage beyond which all later terms stay within that tolerance. This is the heart of the matter. You may have heard that university mathematics expresses this with the language of epsilon. The symbolic form is famous, and sometimes intimidating, but the real content is very simple and very beautiful. Epsilon just stands for a small margin of error. The formal definition says, no matter how small a margin of error is chosen, eventually the sequence remains within that margin of the limit. That is all. Or rather, that is not all, but that is the soul of it. The formal definition does something profoundly important. It turns the phrase arbitrarily close from a loose phrase into an exact logical structure. It replaces the feeling of approximation with a rule about approximation. It teaches mathematics how to talk about endless approach without confusion. And this is why limits resolve Zeno like puzzles. They do not eliminate the infinitely many stages. They explain how those stages can still produce a coherent finite outcome. Now let us move from sequences to sums. Consider again the numbers 1/2, then 1/4, then 1/8, then 1/16, and so on. Each number is smaller than the one before. Instead of looking at the individual terms alone, let us add them step by step. First just the first term. Then the first 2 terms, then the first 3, then the first 4. These running totals are called partial sums, though the name matters less than the idea. The first total is 1/2. The next total is 3/4. The next is 7/8. The next is a little closer still to 1. Each time we add another piece, the total grows, but by a smaller amount than before. The additions continue forever, and yet the total seems to move calmly toward 1. This is one of the great examples in all of mathematics because it trains the mind to accept a new kind of truth. Infinitely many terms are involved. There is no last term. There is no final finite step where the process is complete in the ordinary mechanical sense. And still, the sequence of partial sums converges to 1. So when modern mathematics says that this infinite sum equals 1, it does not mean that infinitely many additions are somehow performed all at once like magic. It means that the finite approximations taken stage by stage form a convergent sequence whose limit is 1. That distinction is essential. An infinite series is not a crude, ordinary sum stretched beyond its natural use. It is defined through limits. The meaning of the infinite sum comes from the behavior of the partial sums. We first create a sequence of finite totals. Then we ask whether that sequence converges. If it does, the limit is the value of the series. If it does not, then the series does not converge to a finite number. This shift in viewpoint is one of the deepest conceptual moves in analysis. Instead of trying to complete an impossible infinite task directly, mathematics studies a sequence of finite tasks and asks about their limiting behavior. Infinity is handled through approximation. Endless process becomes intelligible because each stage is finite, and the overall meaning comes from the limit of those stages. That is precisely the modern response to Zeno. The path can be broken into endlessly many smaller pieces, and still the total distance can be finite. The travel times for those pieces can also shrink in such a way that their total is finite. There is no contradiction once one understands convergence. Infinitely many stages do not automatically imply an infinite total duration or an infinite total distance. What matters is how the stages behave. It is worth repeating, what matters is not only that there are many stages, even infinitely many stages. What matters is the size of those stages and the behavior of the accumulated totals. Now this might tempt us into dangerous oversimplification. We might begin to think that whenever terms get smaller and smaller, the totals somehow settle down. But analysis teaches caution here. Some endless processes stabilize, and some do not. This leads us to a very important contrast. The series made of 1/2, 1/4, 1/8, and so on converges. Its partial sums settle toward a finite value. But there is another famous series made from 1, then 1/2, then 1/3, then 1/4, and so on. These terms also get smaller. They also tend toward 0. But the accumulated sum does not settle to a finite limit. It grows without bound, though very slowly. This is called divergence. So now we have a crucial distinction. Some infinite series converge. Others diverge. Infinite summation is subtle. It is not enough to say that the terms are becoming small. One must ask whether the partial sums approach a stable value. This is one of the most important conceptual points in elementary analysis, and it deserves to be revisited slowly. For a series to converge, its individual terms must tend to 0. If the terms do not even go to 0, then the total cannot possibly settle down. That much is necessary. But it is not sufficient. Terms going to 0 is a requirement, not a guarantee. Let us say that again in a slightly different way. If the pieces of an infinite sum fail to become negligible, the sum has no chance of converging. But even if the pieces do become tiny, they may still add up, over endless repetition, to something unbounded. Smallness of the terms is not the whole story. The rate at which they shrink matters. The structure of accumulation matters. The individual terms and the running total are related, but they are not the same object. This is a profound lesson, and not just a technical one. It teaches us that local behavior and global behavior can differ. A process can have pieces that fade away and still produce a total that escapes to infinity. Conversely, a process can involve endlessly many non-zero additions and still settle to a finite value. Analysis lies in this tension between the local and the global, between the step and the whole, between the term and the accumulated effect. Let us pause and reflect again. We began with a philosophical unease about motion. We then passed to sequences, where endlessness appears as an ordered list of stages. We then passed to series, where endlessness appears as accumulation across infinitely many stages. And throughout, the central idea has been convergence. That is the thread unifying everything so far. Convergence is the language that turns endlessness into intelligibility. Now there is another example, very famous and very emotionally resistant, that helps illuminate the same idea from a different angle. This is the statement that the endless decimal made of 0.9 followed by another 9 and another 9 and so on forever is equal to 1. Many people dislike this statement when they first hear it. It feels like a trick. It feels as though the endless decimal should be just a little less than 1, forever approaching but never arriving. And the discomfort here is valuable. It shows us exactly where intuition collides with precision. What does the endless decimal mean? It does not mean some mysterious object with infinitely many digits physically written out to completion. Rather, it is understood through a sequence of finite decimals. First 0.9, then 0.99, then 0.999, and so on. Each finite stage is less than 1, but each stage is closer to 1 than the stage before. The gap keeps shrinking. And what is the limit of this sequence of finite decimals? It is 1. So the endless decimal is defined as that limit, and therefore it is equal to 1. Again, the point is not verbal cleverness. The point is that infinite expressions in analysis receive their meaning through limiting processes. Once the meaning is understood correctly, the equality is not paradoxical at all. It is simply a consequence of convergence. Still, the emotional resistance is worth respecting. It tells us something about how the mind imagines infinity. We often imagine an endless process as forever incomplete in a way that blocks identification with a finite result. But analysis teaches a more nuanced view. A process may have no final finite stage and yet possess a well-defined limit. The absence of a last step does not prevent the existence of a limiting value. It is worth repeating that, because it is one of the central shifts in thinking about infinity. No last step is needed for a limit to exist. Convergence does not require a final term. Endless approximation can still determine a precise value. This is one reason analytic infinity differs from set theoretic infinity. In set theory, one often asks how many elements a collection has, or whether one infinite collection is larger than another. Infinity there is about size, about cardinality, about comparing collections. In analysis, the emphasis is different. Here infinity often appears as process. One asks what happens as a sequence continues, as a sum accumulates, as refinement goes on without end. So this video, in spirit, marks a movement from infinity as size to infinity as process. That conceptual shift is worth naming clearly. Set theoretic infinity asks, how large is the collection? Analytic infinity asks, what is the behavior under endless approximation? Both are forms of infinity, but they speak different dialects of the infinite. One is static, in a sense, and one is dynamic. One concerns collections all at once. The other concerns motion, accumulation, approach, and stabilization. And convergence is the bridge that makes the dynamic form mathematically tractable. Now let us look more closely at the formal spirit of convergence, still without relying on symbols. Suppose someone claims that a sequence converges to some number. What must be checked? One must check that no matter how demanding the requested accuracy becomes, this sequence eventually satisfies it and keeps satisfying it forever afterward. Not for a few lucky terms, but for all sufficiently late terms. There are two ideas hidden here. First, there is flexibility in the chosen margin. The observer gets to demand any degree of accuracy. Second, there is permanence. After some stage, all remaining terms stay accurate enough. This permanence is crucial. Without it, a sequence could wander close to the limit occasionally and then drift away again. True convergence requires eventual discipline. The sequence must settle. Now, even if one does not yet work comfortably with the formal definition, it helps to feel its purpose. The purpose is to control approximation. Limits are not mystical predictions. They are statements about eventual control over error. That is why analysis becomes so powerful in calculus, differential equations, probability, and numerical methods. It provides an exact grammar for talking about quantities that are approached, approximated, refined, or accumulated. Let us pause and summarize before moving on. We have seen that Zeno's paradox raises the question of how infinitely many stages can belong to a finite act. We have seen that sequences model ordered infinite processes. We have seen that convergence means eventual closeness that can be made as strict as one likes. We have seen that infinite sums are interpreted through the limits of partial sums. We have seen that some series converge and others diverge. And we have seen that endless decimals are also understood through limits. All of these are expressions of one great theme. Analysis studies what happens when a process continues without final termination. There is another advanced but very elegant viewpoint on convergence that is worth mentioning because it deepens the same story. This is the notion of a Cauchy sequence. Instead of asking whether the terms approach some outside target, we ask whether the terms eventually crowd together among themselves. In other words, perhaps we do not yet know the limit, or perhaps we do not wish to name it. Can we still detect that the sequence is stabilizing? Yes. A Cauchy sequence is one in which later terms become arbitrarily close to each other. This is a beautiful idea. It says that convergence can be sensed internally. We do not need to point to the destination first. We can look at the behavior of the sequence itself. If the terms compress together more and more tightly, if the tail of the sequence becomes uniformly clustered, then the sequence is behaving as though it is approaching something. In the real numbers, this intuition is fully justified. Every Cauchy sequence of real numbers converges to a real number. This fact is part of what is meant by saying that the real numbers are complete. Completeness is one of the deepest background properties in analysis. It means, roughly speaking, that the real number line has no gaps of the kind that would prevent internally stabilizing sequences from landing somewhere. Endless refinement does not fall through cracks. When a real sequence becomes Cauchy, the number system is rich enough to contain its limit. This may sound abstract, but conceptually it is very close to everything we have already discussed. Zeno's paradox asks whether endless subdivision destroys completion. The theory of limits says no. The concept of Cauchy sequence says more. If the process becomes internally coherent enough, the real number system guarantees a place for it to converge. That is a remarkable harmony between process and structure. And because we are moving gently through the architecture of analysis, let us mention one more famous landmark, the Bolzano-Weierstrass theorem. This theorem says that every bounded sequence has a convergent subsequence. The full sequence may not settle down. It may oscillate or wander. But if it stays within some fixed range, then hidden inside it there is always a subsequence that does converge. This is another reassuring principle. Even when behavior looks disorderly, mathematics can often extract structure from within it. Analysis does not demand perfect calm everywhere. It shows that under the right conditions, order can be found inside apparent restlessness. That is why the theorem matters conceptually here. It reveals that infinity in analysis is not chaos. It is patterned. It is governed. Even bounded wandering cannot avoid producing convergent structure somewhere inside itself. Let us pause and reflect once more. There is a common emotional image of infinity as something wild, formless, impossible to grasp. And in one sense that feeling is understandable. Infinity does exceed ordinary finite experience. But analysis teaches another lesson. Infinity, when handled carefully, is not mere vagueness. It has laws. It has distinctions. It has stable behaviors and unstable ones. It has convergent sequences, divergent series, Cauchy conditions, subsequences, completeness. The endless can still be structured. This is perhaps why the historical development of analysis was so transformative. It did not remove mystery from infinity completely, but it gave mathematics a disciplined way to work with endlessness without collapsing into confusion. And that returns us quietly to Zeno. Zeno forced the question. If a path can be divided without end, how can it ever be traversed? Modern analysis replies by understanding that endless divisibility does not prevent a finite limit. The infinite list of stages is real as a conceptual decomposition, but the total outcome depends on convergence, not on the existence of a last stage. There is no contradiction in saying that a finite distance can be decomposed into endlessly many shrinking parts. There is no contradiction in saying that the corresponding times can also shrink so that their total is finite. The paradox dissolves not because we reject the infinite decomposition, but because we understand the limit of the associated accumulation. It is worth repeating in a comma in simpler way. Zeno noticed endlessly many steps. Analysis asks about the total of those steps. The total can be finite. That finiteness is expressed by convergence. And convergence is made precise by the language of limits. Now, because the listener may drift in and out of focus, let us gently restate the central ideas once again from another angle. A sequence is an ordered unfolding, one stage after another. A limit is the value that the sequence gets and stays arbitrarily close to once we go far enough. An infinite series is interpreted through the sequence of its finite partial sums. Convergence means those partial sums settle toward a finite value. Divergence means they do not. Terms shrinking to zero are required for series convergence, but they do not guarantee it. Infinitesimals also receive meaning through the limits of finite truncations. Cauchy sequences show that convergence can be detected internally. Completeness ensures that such internal stabilization has a destination in the real numbers. And bounded sequences, even if unruly, still contain convergent subsequences. All of this belongs to one great theme: endless approximation can produce exact mathematics. That phrase is worth dwelling on. Endless approximation can produce exact mathematics. At first that sounds contradictory. Approximation seems loose. Exact seems strict. But the theory of limits unites them. By controlling approximation with arbitrary precision, mathematics turns approximation itself into something exact. A limit is exact not because the process stops, but because the approach can be made precise beyond any chosen tolerance. This is one of the quiet triumphs of human thought. Now let us make one more contrast between ordinary intuition and analytic thinking. Ordinary intuition often asks, has it arrived yet? Has the process finished? Is there a final step? Analysis often asks a different question: what is the limiting behavior of the finite stages? That shift changes everything. It allows mathematics to treat processes that never terminate stage by stage and yet still yield determinate outcomes. This is why calculus becomes possible. Derivatives, integrals, infinite expansions, numerical approximations, all of them depend on this disciplined understanding of limit. The theory of limits is not a side remark in mathematics. It is one of its foundations. But even at this more reflective level, it is good not to lose the original human feeling of the paradox. Zeno remains valuable because he reminds us that motion, continuity, and completion are not conceptually trivial. What feels obvious in experience may conceal enormous depth in thought. The act of crossing a room can lead, if examined carefully enough, into the foundations of analysis. That is a beautiful thing. The ordinary world and the infinite world are not as far apart as they seem. A footstep contains philosophy. A race contains analysis. A decimal expansion contains a lesson about limit. A shrinking sequence contains an entire theory of convergence. The infinite is not always far away. Sometimes it is hidden inside the structure of the familiar. Let us now begin to close slowly with a unifying summary. We began with Zeno's paradox because it exposes a tension between motion and endless subdivision. If every journey can be broken into infinitely many prior stages, how can any journey end? This question feels disturbing because it confronts us with the possibility that the ordinary world may rest on something conceptually impossible. Modern mathematics does not dismiss this concern. It answers it by developing the notion of limit. A sequence shows us how a process unfolds step by step. Convergence tells us what it means for such a process to settle toward a value. The formal spirit of the epsilon definition explains that approaching means eventual closeness under any demanded accuracy. Infinite sums are then understood as limits of finite partial sums. Some such sums converge, as in the geometric example of repeatedly halving. Others diverge, as in the harmonic example, even though their terms still shrink to zero. Infinite decimals also fit the same pattern, and that is why the endless decimal of repeating nines equals 1. Cauchy sequences reveal that convergence can be recognized by internal clustering, and completeness of the real numbers guarantees that this clustering leads to an actual limit. Bolzano-Weierstrass shows that boundedness itself already contains a promise of convergent structure somewhere in sight. So the broad lesson is this. In analysis, infinity is not primarily about the size of collections. It is about process. It is about what happens when refinement never stops, when approximation continues forever, when accumulation unfolds without a final stage. Limits are the language that make this world understandable. They let mathematics say, with full precision, how endlessness can still produce order, structure, and finite outcomes. And perhaps that is the most soothing thought in the whole subject. Infinity does not always destroy clarity. Sometimes, when approached carefully, infinity is exactly what reveals clarity. The endless can be lawful. The unfinished can still have a definite tendency. The never-ending can still possess a precise meaning. So when Zeno asks how motion is possible if there are infinitely many stages, analysis answers with patience. Yes, there may be infinitely many stages in the description. No, that does not force the total to be infinite. What matters is convergence. What matters is the limit. What matters is how the process behaves as it continues without end. And with that, the paradox becomes not an obstacle, but an entrance. An entrance into analysis. An entrance into the mathematics of approximation. An entrance into the idea that forever, handled properly, can become intelligible. Let us leave the subject there gently. A path may be divided again and again. A sequence may continue without final term. A sum may receive endlessly many additions. A decimal may stretch on without end. And still, through the condiscipline of limits, mathematics can understand what these processes mean. That is the quiet power of analysis. That is how endlessness becomes something the mind can hold. And that is why Zeno's paradox, ancient and unsettling, still leads us into one of the most beautiful ideas in all of mathematics.